So, so, good evening. Hello. Okay. Yeah. So, good evening, everyone. So, tomorrow is MTRP. Any one of you participating? Uh, I guess Shankarda shared that link, right, in the WhatsApp group. I also had it for my status a few weeks back. Okay. So, for that, let's. So, I haven't started any new topics for the last month or the last 2 months, I guess. So, today, let's start with inequalities. We can continue with geometry later on after digressing a bit. So inequalities. So this is relatively a small chapter. You will just need to remember the few of the most used inequalities. You can just do them with just the first three of them, like the arithmetic mean, the geometric mean, and the harmonic mean. So these, as you know, are the pretty self-explanatory. They're the means. Like if you have A, B, C, three numbers, then the central element B. So B can be expressed as A plus C by 2 if this is an AP. While at the same time, B is equal square root of AC if originally the sequence was a geometric progression, and B is equal to 2 by 1 by A plus 1 by B if it was a harmonic progression. Right, so that's why we get the arithmetic mean as sum over xi. Suppose we have n observations. So these A, B, C values, we call them as, they're called observations. This is, sorry. This product over xi is over 1 by n. And the harmonic progression is n by sum over 1 by xi. So other than these three, we also have the quadratic mean, which is square root of sum of squares by n. So if you have a vector, so x vector is x1, x2 octal, xn, then you can find the quadratic mean of this vector is the largest among the four. It's greater than the arithmetic mean, which is in turn greater than the geometric mean. And the smallest one of them is the harmonic mean. Right, so these are the results. So how can we prove these? So suppose I just want to prove the second condition, the arithmetic mean greater than equals to geometric mean 1. So suppose we want to prove it by induction. So if you're able to show somehow that a plus b by 2 is greater than or equal to square root of ab, call the statement P2. Then we can go to P4, P, P2, P6, and like that up to for all even numbers. That you can place any. Okay, so let's see. First, let's show how to prove this. So we can use a plus b whole square greater than or equal to 0. So using this information, we can say a squared plus b squared is greater than or equals to minus, okay, so let's make it minus a minus b. That's minus 2ab greater than or equals to 0, which is a squared plus b squared greater than or equals to 2ab. So instead of a and b, let's substitute square root of a and square root of b. So it's basically square root of a minus square root of b squared greater than or equals to 0. So P2 holds. Now with induction, suppose, so assume or let's say induction hypothesis. We have Pn to be true. Okay. Or maybe we should go the other way around, like from Pn to Pn minus 1. Let's just a minute. So hypothesis is Pn is true. Now let's check for P2n. So P2n has these observations. So the vector x now has x1, x2 up to x2n, and we can pair them up like a1, a2, sorry, x1, x2, x3, x4, like that up till x2n minus 1, x2n. So this is the sum. This thing is greater than or equal to, now applying P2 on each of those pairs. We get this. Now you see you have instance. So now we can consider a new vector y equals to, it has n observations. The first one being square root of x1, x2. The next one is square root of x3, x4 up till square root of x2n minus 1. x2n. So this is in r power n, a vector with n coordinates. So applying Pn on this vector, we get sum over square root of xi plus 1. I runs from 1 through 2n minus. So the way to write it is x2i, 2i minus 1 to I runs from 1 through n. So this by n is greater than or equal to our statement. This is our statement Pn. Okay, so I haven't written it down. So Pn says exactly this thing. Yeah, so using Pn here, we are able to say sum over I runs from 1 through n, xi is greater than this thing, which is twice sum over square root of 2i minus 1 x to y, which is greater than n times product over x to I minus 1 x to I whole power 1 by 2n, which is, so that implies sum over xi by n product over 1 to 2n x. So let's call it k now, because we are placing 2i with 2i with k. So this was Pn. Pn implies P2n, but this doesn't. So this isn't enough. You see, we're able to like conjecture P1 will, since we already know P2 is true, so that will imply P4 is true, and that will imply all multiples of 2 for n in for all those all those values of n which are divisible by 2. Only those for only those values this inequality holds. So you just have to extend it for the odd numbers, and to do that we will now prove. Now show Pn also implies Pn minus 1. So it's like jumping by a step of 2 and then going back to fill up the gaps. So this is a kind of a new trick, a new kind of induction. I mean, the induction, the steps are the same, but yeah. So this is called Cauchy's induction. So names aside, to do this, we're introducing a new variable g, which is product of I runs from 1 to n minus 1, xi power 1 by n minus 1. This is a geometric mean of the first n minus 1 observations. So we want to prove Pn minus 1. So let's first assume, as before, that assume Pn is true again. So you just have to reduce one of the observations to make it Pn minus 1, right? Seems easy enough. So this is Pn. Now we substitute this G as the xnth observation. Substitute xn equals to G. What happens here is we are left with x1, x2, x3 up till xn minus 1, which is G power n minus 1, and the last element is G itself. This is basically just G. So let's keep it like that for now. So x1, x2, xn minus 1 is greater than is ng minus g and minus 1g. And g, as we know, it's n minus 1th root of x1, x2, x3 up till xn minus 1, the product of the first n minus 1 numbers. So here we have, this is squared for now. Just a minute, my laptop is running out of battery. So Pn implies Pn minus 1. So this is observation 3. This was observation 2. And yeah, this was observation 1. So using these three observations, using 1, 2, and 3, by the principle of mathematical induction, Pn is true for all n. So that's done for AMGM inequality for now. By the way, there's a totally different way of proving this, like using quadratic formula. So let's have a look at it. Okay, we will have a look at it next time. Okay, before these schemes of inequalities, there are also other very basic ones that are. So let's solve some of them first. Game theory. So before that, we have the triangular inequality. This is due to the vector addition you can think of. If you have two vectors of length A and B, then the third side, which is the vector sum of so vector sum of these two sides. So this angle, let this be theta. So you have vector A plus vector B is the magnitude, so you can take mod is less than or equal to, right? So this is some form of triangular inequality. This also holds for normal real numbers since they are just one-dimensional vectors. And also holds for higher dimensions, but we need more machinery to prove that. You can extend it to the n form. And this is actually a generalization, a specific case of a more general inequality called the Jensen's inequality. Which deals with convex functions. Suppose fx is a function, is a convex function, or let this be any continuous function. So we know, so let me first demonstrate it. So if fx is equals to mod x, we know how the graph of mod x, y equals to mod x looks like, right? This is just two pair of 45-degree x equals to y and x equals to minus y. So this is obviously convex. So what is the idea of a convex function? Well, a closed simple curve is convex if you have between any 2 points, the line joining those 2 points totally contains, exclusively contains points inside of that curve. So if you have a closed simple curve, you can designate the surface on which it is drawn as inside and outside. So here, as you can see, for the 2 points A and B, the line partly passes through points which are outside. So this is not a convex shape or curve. So in the case of graphs, the inside part is the upper one, upper half, and everything else is outside. So this is the inside, the shaded part. So if you take for this our y equals to mod x graph, if you take any 2 points, you can see it's always stayed inside. Like there's no way to pick 2 points inside the graph and having the line pass through outside. So this is a convex. So this is convex function. So functions like this are all convex, right? But this is a concave function. So easier way to remember is whether this, if you pour water from the top, suppose it rains and the water gets collected in here. So whether or not it holds water, if it holds onto water, then it's convex. Otherwise, if the water runs off, it's concave. Or you can think of it as a cave, an entrance to a cave. If you're getting the hunch or the imagination. So yeah, so now we can say, so now let's pick 3 points. These are the corresponding functional values for the points x1, x2, and x3. Or we don't need 3, we need just 2 of them. x1, just a and b. Okay, x1 and x2 for now. So join it with a line, take the midpoint. This is our so this height is our fx1 plus fx2 by 2. So midpoints can be expressed as the arithmetic mean of the endpoints, right? So this line has a midpoint which is equal to fx1 plus fx2 by 2. Also, if you pick the midpoint along the x-axis, so this point is x1 plus x2 by 2, and then get the corresponding y value, you get f of x1 plus x2 by 2. So you can obviously see the function of the mean is lesser than in height than the mean of the function. So fx1 plus x2 by 2 is less than or equal to fx1 plus fx2 by 2. So this is when f is convex. can be generalized to f of sum over I runs from 1 to n xi by n less than sum over fxi by n. This is when convex, and exactly the opposite happens when f is concave. So putting f equals to mod x, we get back the triangle inequality. Right. So, so now let's solve some problems. So show that given xy positive, square root of x squared by y plus square root of y squared by x is greater than or equals to square root of x square root of y. This is just plain and simple AMGM, as you can see. So the sum is greater than or equals to twice square root of x squared by y times y squared by x square root. So this is power 1/4. X and x gets cancelled, so does y and y. So we have xy. Okay, so no, it's not this easy. Well, there is something called rearrangement inequality, and we can exploit that. So rearrangement So suppose like if you have some observations x1, x2, x3 up till xn, and so you have these observations. You make a matrix, make a permutation matrix out of it. So the top row has the elements as they are as is, in any order you can see. Now you just take any random permutation of these n elements, say suppose xi1, xi2 up till xin, and take another permutation xj1, xj2 up to xjn. Typically, we don't write permutations like this, so we can say like sigma or pi is a permutation. So it's like a mapping from the set 1 to n to itself, which is pi is a bijection. Then we can say ik is equal to pi k. Similarly, we can have another one like pi 1 and pi 2. So we can say jk is equals to pi to k. Right, so now we have got a matrix. You can have two columns, minimum two columns. Sorry, minimum two rows. You can have many more of them. And now you just take product or apply any other convex function. So let's use product for now. So then you can say the sum of the products. So xi1, we write it in long form. So x1, xi1, xj1 plus x2, xi2, xj2 up till xn, xin, xjn. So this is less than or equal to x1 cube, x2 cube up till xn cube. So you see, this is the rearrangement inequality. So if you have so initially these xi's have to be in order. So x1 less than or equals to x2 less than or equals to x3 up till less than or equal to xn. So if they are in order, and now you permute the order and then take product and sum, it's always less than or equal to what you might have got if you had taken all the three rows in the same order, in the increasing order. So example, if you take 1, 3, and 5, and you take 1 squared plus 3 squared plus 5 squared is greater than or equal to, if you multiply it with like 5, 1, 3, you get 5 plus 3 plus 15, which you can obviously see is smaller. So using that, we can, so for n equals to 2 case, this basically boils down to if you have two sets of observations, A and B, X and Y. So if you take A, B, and X, Y, that would be greater than or equal to if you reverse the order. So AX plus BY is greater than or equals to AY plus BX. So here in this case, it's also easier to see other ways, like if you can do many things. Okay. So let's bring everything onto one side. AX minus BX plus BY minus AY. So taking common X, we have A minus B. Taking common Y, we have B minus A. So this is A minus B times X minus Y greater than or equals to 0, which is true since this is a positive quantity greater than or equals to 0 because A is greater than or equals to Y. I mean, this will be greater than or equal to as long as this is greater than or equals to. Similarly, this. So using this result, this inequality, we can now solve our our problem. So here you can take square root of x So we can assume without loss of generality that x is greater than y. That would imply square root of x is greater than square root of y, and 1 by square root of x is less than 1 by square root of y. This is first observation, and also x squared is square root of x squared is greater than square root of y squared, right? Using these two. So this is, suppose a, this is b, this is x, this is y. Put it in here. Sorry, this is not x, this is x, this is y. So you got square root of x squared by y plus square root of y squared by x. This is in order, so this is greater than or equals to 6 squared by x plus y squared by y, which is just square root of x plus square root of y. So that proves this inequality. Okay, next try to show. A, B, C, D are real numbers such that a plus d is equals to b plus c. Try to show a minus b times c minus d plus a minus c times b minus d plus d minus a times b minus c is greater than or equals to 0. So try it for 5 minutes. We'll be back at 10. So I'm back. So, so how to solve this one, right? Cyclic sum of A minus B C minus D. You can multiply everything out and then try to use this equation. Without doing that, we can write it as A minus B is equals to C minus D. So that brings, this is just A minus. So that implies it's A minus B squared plus A minus C, B minus, or we can also say B minus D is A minus C. So this is A minus C squared. And only the last one is this is an if and only if statement. A plus D equals to B plus C, right? Okay, let's try to multiply everything out. So AC minus BC minus AD plus BD plus AB minus AD minus CB minus CD plus DB minus DC minus AB minus plus AC. This is plus. So this is greater than or equal to 0. So if and only if statement. Got AD, AD. So minus 2 AD, AC, AC plus 2 AC, BC, BC minus 2 BC, BD, BD plus 2 BD, DC, DC cancelled, AB, AB cancelled, and I guess AD was already paired up, so right. So this is all that we have got. Let's see if we can factorize. So 2 is common. You can take common A, C minus D plus B, D minus C. So twice A minus B times C minus D. And A minus, so if and only if 2 can be cancelled. A minus B is C minus D. So yeah, and this is true. So which is true for all A minus B in R plus in R. So until and unless we land down to some complex numbers, we can't have negative squares. Next. So show that x plus y times y plus z times z plus x is greater than or equal to xyz times 8. So how to show this? So you apply AMGM for two observations. On each of the factors of the LHS, you get 2 square root of xy, 2 square root of yz, 2 square root of zx, and just multiply to get 8xyz. One line, right? Next, suppose we have, oh, by the way, for AMGM, there is an additional condition. So I forgot to mention. Xi's need to be positive. We need to be in R plus. Keep this in mind. Every time you see a problem which handles XYZ in R, represent X as X plus minus X of minus, like this way. X equals to X plus minus X minus, where X minus is mod R 0 if X greater than 0 and minus X if X less than 0. X plus is the opposite. X when X greater than 0 and 0 otherwise. Okay, so keep that in mind. Next we have X squared plus yz plus zx. So this whole thing. Or you can directly use rearrangement inequality with x, y, z and y, zx. So this is certainly smaller than x, y, z and x, y, z. X, y, y, z. With AMGM, you need to add weights. So weighted AMGM inequality. So weighted digression. This is a digression. Weighted so if you have observations x1, x2 up to xn, along with that a weight vector w, W1, W2, Wn, then just take a dot product or sum over xi wi by sum over wi. This is greater than or equal to product over xi power wi sum over wi. So this is the weighted AMGM inequality. Using this, we can add halves as weights. So this is half times x squared plus y squared plus half times y squared plus z squared plus half times z squared plus y squared. Each of them being greater than or equal to square root of, sorry, not square root of, just half times twice xy, which is xy. So this is greater than or equals to yz. This is greater than or equals to zy. So the whole thing is greater than or equals to xy, yz, zy. So there are two different methods of solving this one. Using AMGM, sorry, weighted inequality isn't needed as such. Last one, this is x squared plus y squared plus z squared greater than or equals to x times y squared plus z squared plus y times x squared plus z squared. So the idea is kind of similar. You club, so you have to club x squared along with that y squared plus z squared. So now you have two observations basically. One is x squared and the other one is y squared plus z squared. And you can just write x squared times, which is x times root over y squared plus z squared. So you can take y squared out and y squared plus x squared. Sorry. Z squared plus x squared. This is y times z squared plus x squared. Add them up, you get this. Okay. This is the last type of problem. Okay, suppose you said A, B, C are positive reals. So what's the minimum possible value of the sum of the four numbers with the product? So the product of the sum of the numbers and their reciprocals. Like this would be 16. So why is this 16? The first we need to apply MGM on the first 4 observations. We get 4 times fourth root of ABCD. And then again on the next factor, we get 4 times fourth root of 1 by ABCD. Then multiply these two. It's already greater than or equal to, so 4, 4, 16, and the factors get cancelled, so 16. So you can generalize this to like x1 plus x2 plus xn times 1 by x1 up till 1 by xn. This is greater than or equals to n squared. Right. Now can you show this one? Everything is positive. Given a plus b plus c is 1. So you might be tempted to show each of them is greater than or equals to 4 somehow, since 4 cubed is 64. But then we won't be using this fact. Okay, we might be able to use, let's see. So 1 by a plus 1, a plus b plus c by a plus 1, which is b plus c by a. Which is a plus b plus c by a. Okay. Which is 1 by a. Kind of weird. Sorry, I guess I did a mistake somewhere. Yeah. This was, so it's just 2. If we multiply out everything, we have a, b, c, 1 by A, 1 by B, 1 by C, plus 1 by AB, 1 by BC, 1 by CA, and lastly 1. We can use harmonic inequality on these three and get 3 by cube root of EMGM only. So this is the arithmetic mean, so geometric mean will be so that means is greater than or equals to 1 plus 1 by ABC plus 3 by cube root of ABC plus 3 by cube root of ABC squared. Uh, we can rearrange it as so this is basically 1 plus 1 plus 1 by cube root of ABC whole cube. So you have the a squared term, the a cube term, this is the b cube term. This is the 3a squared b. This is the 3a squared b term. This is the 3ab squared term. So you have all four terms. So this is 1 plus 1 by 3 squared cube root of ABC whole cube, right? We need to get the lower limit of 64. So we somehow have to show this is greater than or equals to 4 cube. So we have to make how to do that. So this is equivalent to saying oh no, this is obvious. So 1, which is a plus b plus c, is greater than or equals to thrice cube root of ABC. This is just EMGM. So proved. So on homework, show that the minus form is greater than or equals to 8. Okay. This is your homework. Next, continue with our problems. Okay, Nesbit's inequality is next one. So Nesbit's inequality. So it says if ABC if ABC are positive reals, and we have A plus B by C plus A plus C by A plus B. Sorry, A was A by B plus C. This is greater than or equals to 3 by 2. So how to show this? We can assume without loss of generality, A is less than or equals to B less than or equals to C. And that would mean A plus B is the smallest, followed by C plus A, followed by C plus B. That would imply their reciprocals are in the opposite order. So now let's use the rearrangement inequality. So you have the matrix ABC, and so A plus B, B plus C we don't have. Oh, sorry, we have B plus C and we have C plus A. So this is C plus B. This is C plus A. This is A plus B. So from our assumption, we have A less than or equals to B less than or equals to C. And from this one, what we just showed, we have this less than or equals to this less than or equals to 1 by A plus B. So this is the ideal. Both the orders are the same, so this is the maximum out of any other permutations. So this is greater than or equal to we might permute the top row now. So BCA, C plus B, C plus A plus B. So that implies A by C plus B plus B by C plus A plus C by A plus B is greater than or equals to B by C plus B plus C by A plus C plus A by C plus B. Sorry, this was A plus B. A plus B. And there we can take another permutation, which is CAB The next row is fixed. And this would also result in the same c by a plus b, a by c plus a, b by a plus b. Okay, not the same, but similar. Sorry. So we got 1 and 2. We add them up. That implies twice the left-hand side. Remember, we needed a 2 in the denominator, so we are multiplying. You can think of it as a multiplication by 2 on both sides. So we need to show the right-hand side is greater than or equals to 3 now. C by a plus b. Oh, sorry. This was c by c plus b. C by c plus b, b by c plus b. You get 1. A by a plus b, b by a plus b. You get 1. C by c plus a by c plus a, you get 1. So this is 3. So that's what we get. 3 by 2. So that proves Nisbet. Okay, now question. Show that this is from IMO 1995, by the way. So ABC again positive reals with ABC, A times B times C equals to 1. Show that 1 by A cube B plus C plus 1 by B cube C plus A plus 1 by C cube A plus B greater than or equals to 3 by 2. So try it for a minute. We'll be back in 2. Okay, so if you try to use Nesbit inequality here by writing it in this form, you might face some difficulties. So I couldn't do it actually. Like I tried to write it as how would you write it? Like here you have the numerator as power 1 and the denominator as power 1. So both the numerator and denominator have the same power here. But in this expression, all the powers are in the denominator, nothing is in the numerator. So if you take 1 by a squared and 1 by and a into b plus c, the power does balance out to 2. But now you have what are the observations now? So I guess you have to do it again from the scratch using the basic principles like rearrangement inequality. So let's assume C less than or equals to B less than or equals to A without loss of generality. Then we have X. We can take X as 1 by A, Y as 1 by B, and Z as 1 by C. So that means we have X squared by 1 by Y plus 1 by Z plus Y squared by 1 by X plus 1 by Z plus Z squared by, sorry, not squared, cubed. And you know ABC is equals to 1. So that means XYZ is also equal to 1. Okay, using that, maybe we would be, so if we had written it as A squared by AB plus BC, and well, that is ABC by A squared. So BC by A it's still not lining up. Okay, let's continue. This is equal to x cubed by x times y plus z. I'm not writing it all every time, it's just from now on we'll be using the cyclic notation. So that is x squared by y plus z. So this is as far we can get. At this point, I used rearrangement inequality twice back in Nesbit, back while proving Nesbit. So let's do the same thing. We can take x squared, y squared, z squared, and x plus y. So we had assumed this one, that implies x greater than or equals to, sorry. So A is the smallest, right? And that implies x plus y, y plus uh, z plus x and z plus y. That would imply 1 by x plus y is the largest, followed by z plus x and z plus y. The smallest one is the y plus z. This is the largest combination. Anything else is smaller. Okay, instead of x square y square z square, we can take x, y, z and x, y, z. And now in here we can flip the second row. So x, y, z, y, z, x. And the last row is the same. Similarly, we can write it as x, y, z, z, x, y. Again, the same last row. This is also same. Then add them up. You get so twice x squared by y plus z plus y squared by z plus x plus z squared by x plus y greater than or equal to xy plus xz. So you can take common x, y plus z by y plus z. X plus z by x plus z. Z times x plus y by x plus y. And finally, using substituting it back to ABC, sorry. So denominator is 1. This is again 1. So finally this is 3 by 2. Taking this 2 down. Proved. Okay, now let's learn about another new inequality, Chebyshev's inequality. Chebyshev. I guess I'm getting the spelling right. Chebyshev's inequality. So if you have x1, x2, x3 unordered in the increasing order. Similarly, y1, y2, y3. Then you have their dot product by n greater than or equal to the product of the arithmetic means. So the proof is using rearrangement inequality n times. So on the left we have x1, x2 up till xn. This is proof. And y1, y2 up till yn. This is the largest arrangement or permutation. Anything else, like we can take x1, x2 up till xn, and for the first one we take it the same thing, yn. So then this is more aptly written as equal to. Next we will rotate it 1 by onto the left, so y2, y3 up to y1. Next again y3, y4 up till y2, like that up till the last one will be totally the reverse. x1 yn, x2 yn minus, sorry, y1 xn yn minus 1. Adding all these up, the left hand side is repeated. So we have got n times x1, y1 dot up till xn, yn, the dot product. And the left hand side we have all kinds of combination, all the impossible permutations, right? So it's sum over x1, x2, x3 up to yn times y1, y2, y3 up to yn. So x1 is multiplied with each of y1, y2 up till yn. And lastly, we can divide both sides by n squared to get the final result. So we can use the Chebyshev inequality to prove the QM-AM inequality. Or even you guys can try this at home. So homework 2, prove quadratic mean arithmetic mean inequality using this Chebyshev. Okay, so it's almost 11, so I will call it a day now. Bye. Good night, everyone. I will upload the notes and recordings also. Okay, bye.